For a t-test, though, you're only looking at one beta. You have to pick one. Only one beta. Beta I here is just a way of subscripting betas. You would actually have to put in which beta you're testing. Again, you're using the population parameter when you're stating the null hypothesis and the alternative hypothesis. You're not using the beta hats. Your t-statistic is still your observed beta, in theory, minus 0, because that's your null, and then divided by the standard error of that beta. You're given the standard error of that beta in printouts. I've shown you how to calculate it for the simple linear regression case. For the multiple linear regression case, it will have to be given to you. And here we reject the null hypothesis if the p-value is less than alpha, or if t is less than or greater than, depending on which side of the distribution you are, from the critical value. The degrees of freedom for the t also follow the same degrees of freedom as the mean squared error. So it's the number of observations minus the number of x's that you have minus 1. So it has the same degrees of freedom as the degrees of freedom in the denominator for the f statistic. And so here we find the critical value to be 2.11. And we would say that if the observed t is either less than negative 2.11 or greater than 2.11, we would reject the null. We go to the table. We have one t-stat here of 0.51, so there we would not reject the null. We have another one that's at 7, which is clearly bigger than 2.11, so we reject the null there. And we have another one at 3.2, which is also bigger than the critical value of 2.11, so we reject the null. Or we can just look at the p-value and say, is that p-value less than 0.05? In these two cases it is. In the case for the constant, it is not. So in both of the cases for the slopes, we can reject the null hypothesis, but we can't reject the null for the constant. Alright, multicollinearity. This is something you should be aware of, but you won't learn how to test. Multicollinearity says that your x's that you use are correlated. So your observed x's are correlated with one another. The problem with doing that, or having these x's that are correlated with one another, means that your standard errors for both of them are going to increase. The way to think about that is when you have two variables that are independent of one another. I want to know the variance of x1 given x2. Think back to your Bayes' law stuff. If I say given and they're independent, this is just equal to the variance of x1, because x2 doesn't give you any extra information. However, if they are correlated, then you have to add a covariance term. If they are correlated, this is the variance of x1 plus the covariance of x1, x2. So that makes your standard error, the thing down in the denominator, bigger. And as it becomes bigger, what happens to your t-statistic? It becomes smaller, right? If your standard error becomes bigger, your t-statistic becomes smaller, which means you become more likely to reject or less likely to reject? Less likely to reject. So this is that situation I was telling you where you can have your t-statistics fail, but your f-statistics say, no, the line is significant. If you have a lot of multicollinearity, your individual t's may end up failing. It may end up saying, no, these are not different from 0. But what it's doing is that it's picking up the correlation between the x's, and it's causing those standard errors to get bigger. However, the f-test looks at them all together, so it can parse out this covariance term. It can get rid of that covariance term and say, as explanatory variables, are they good explanatory variables? And you can get an f that's significant even though the individual t's are not. So if you included things like IQ and GPA in the same regression equation, you would think those things are correlated with one another. So because of that, the standard errors associated with both those things would get really big. A key way to know in practice if you have multicollinearity or you suspect multicollinearity, run the regression equation, including both, and then just drop one of them. If the t-statistic all of a sudden explodes really big, you know it was multicollinearity that was eating it up, right? Because it was picking up information from that other variable. So when the independent variables are highly correlated, and what we mean by that is that their correlation is something that's greater than 0.7. It is not possible to determine the separate effect of any particular independent variable on the dependent variable, although their joint effect may still be significant, so thus the f-test could still come out to be significant. If the estimated regression equation is to be used only for predictive purposes, multicollinearity is not a serious problem. So all you want to do is prediction, then you really don't have to worry about that too much. That's great if you're going into finance or if you're going into CIS or something like that, where most of the time the models you're looking at are for predictive purposes. You want to be able to predict stocks. You want to be able to predict purchases. You want to be able to predict hacks, things like that. If what you want to do instead is a causal relationship, then it becomes a problem. Right? Every attempt should be made to avoid including independent variables that are highly correlated. The easiest reason for not wanting to do that is you're just getting redundant information. Right? If two variables are correlated at 70%, or even worse, 90%, that means you're already getting that same information from another variable. So why include both of them? The procedure for estimating the mean value of y and predicted value of y in multiple regression is similar to that of simple linear regression. You give us x's, we plug those x's in, we get a y hat, and we construct a standard error. So we substitute the given values of x's in, we get our y hat, and we construct our predicted value. Now, how we make the actual intervals for multiple regression is outside of the scope of this book. You can do it for simple linear regression. I showed you how to do that. You have the formulas for that. But for multiple regression, it again requires figuring out that big x prime x inverse matrix, which you're not supposed to know yet. All right, so software packages are able to do this under the hood very quickly and can just spit out the actual standard errors that you would need.